So we're going to start with an example for how to find Riemann sums. And down here is the equation for finding a Riemann sum. And the example problem that we have is the integral from 1 to 2 of x squared plus 1 dx, where n equals 4, so there's 4 rectangles. And to find delta x, you just do b minus a over n, which is 2 minus 1 over 4, which equals 1/4. So this is the graph of x squared plus 1. And we have 4 rectangles, which we already drew in, and each base is 1/4. And we're going to do left sums in this problem. So we're starting with 1 and using 1, 1.25, 1.5, and 1.75. But if we were doing right sums, we would start with 1.25 instead of starting with 1. So now you're going to find the area of each one of these rectangles. And to do that, you just take the width, which is 1/4 for each, and multiply it by the height. And to get the height, you just take each one of these x's and sub it into the equation. So for each rectangle, the area is going to be f at whatever x multiplied by delta x. So we just pulled out delta x to make it easier. And we have delta x multiplied by f at x sub 0 plus f at x sub 1 plus f at x sub 2 plus f at x sub 3. And then you just sub in your x's and your delta x, and you get this. These are the numbers that you get when you sub in the x values into the original equation, and then you just simplify, and your answer is about 2.968 units squared. Again, if you're using right sums instead of left sums, the equation would be delta x multiplied by f at x sub 1 plus f at x sub 2 plus f at x sub 3 plus f at x sub 4. Use trapezoidal rule instead of using rectangles. You just have to use the area of a trapezoid instead of the area of a rectangle. And the area of a trapezoid is base 1 plus base 2 divided by 2. Another way to solve for the area is by using anti-differentiation. So if you know the equation, then you can use that. But if you do not know the formula, then you can just use the rectangles. But this way will give you a more exact answer. So you just find the antiderivative of this, which would be 1/3 x cubed plus x evaluated from 1 to 2. So that would be 1/3 times 2 cubed plus 2 minus 1/3 times 1 cubed plus 1, which is equal to, so after you simplify, you get 14/3 minus 4/3, which is equal to 10/3, and that's equal to about 3.3 repeating. And that answer is the more exact answer, because this would be like using a limit, whereas the rectangles, we only use 4 rectangles. So if we used an infinite amount of rectangles, we would probably get this answer.
GFB, Riemann, no gimmicks.
To find the whole area under the curve, under the curve, under the curve. To find the whole area under the curve, under the curve, under the curve. Interval
A to B,
f of x.
stay with me.
F of x, 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 f of x. I have a curve at all angles. I'm using rectangles to find areas, so I use slices 1 to n. Well, if you want slices, this is what I'll tell you. Each little width is b minus a over n. A cos width is changing on the x. It's delta x and height f of x sub I from the middle, or the right or left, because you're evaluating from the eye of the slice you are calculating. Hey!
Areas from multiplication and the base and the height give me some adulation. I know you got some sigma notation where your slices add up in a big summation, so the BCE won't disagree. Let me decree Archimedes. He had the same idea in ancient Greece, but it feels exhausting without Riemann. Kind of a kid, summon the bits with more cunning and wits and breakdance skits and get on it. It's all working out, you don't shun it. I just set up my summation, time to sum it.
And this looks like a job for Riemann. Add it up from A to B, and the more slices that you see can increase your accuracy. And this looks like a job for Riemann. Add it up from A to B, and the more slices that you see can increase
nicest. The smallest of sizes will be the precisest. Infinitesimal bits will entice us till someone comes along with a vision and yells
Switch!
A visionary vision of area to start the transformation. Summation is changing with limits and it's getting greater so fast that it's a fact that I know that those little slices outlast. Time to count them, such a catastrophe, cause there can't be enough time to count to infinity.
But step back and
That's not what the metric truly thinks between the letter D for delta, a differential translator. The new sigma notation, slimmer is better and it's the best thing. The F thing suggesting, divesting X of the sum I am stressing.
Anti-derivative.
When I mention integral of fxd, X who made sense and 10 from A to B. I knew 10, not him, no, not Cauchy. No,
This looks like a job for Riemann. Add it up from A to the N. The more slices that you see can increase your accuracy.